have another method for solving linear differential equations. I think you'll like it better. Most people do. But, well, we're going to build on the old one when we get further in the class, so you do need to know it. But for this specific kind of differential equation, you can use this if you want. And it also does have limitations where sometimes you get something that's wrong. So, but let's practice it. Okay, so it says to find an explicit solution to a linear differential equation. I moved the y term to the left here. First, you compute something called an integrating factor, mu of t, and you calculate that by doing e to the integral of g of t dt, where g of t is the t stuff that's attached to y. Note that you only need one integrating factor, so when you're calculating that integral, just take the most convenient choice for the arbitrary constant, typically 0 if it's plus c, or if it's 1 if it's like k e to the t, something like that. And then we can determine solutions to the differential equation by multiplying both sides by mu of t. Once you multiply both sides by mu of t, you're going to go, oh, I see the product rule, which is going to make integrating both sides easy. Okay, so let's do one. Find a general solution to the differential equation by using an integrating factor. So first thing we do is we find mu of t, which is e to the g of t, e to the integral of g of t dt. I just told you. That's how you find an integrating factor. E to the integral of g of t dt. We choose mu because it's going to force, we choose it that way because it'll make the product rule pop out every time. All right, so in this case, what's g of t? 3. Okay, so this is a pretty simple e to the integral of 3 dt. All right, so what's the antiderivative of 3? 3t. And I'm not going to write plus c because I only need one integrating factor for mu of t. So I'll just choose c to be 0. All right, so my next step is I rewrite my differential equation. dy dt plus 3y equals t. And then I'm going to multiply both sides of my equation by the integrating factor I just figured out, e to the 3t. On the left, I'm going to distribute e to the 3t. So I have e to the 3t times dy dt plus y times 3e to the 3t equals te to the 3t. So change the order of the multiplication here a little bit to help us recognize the product rule. So you might, when you look at the left-hand side of this equation, we've got e to the 3t times the derivative of y plus y times the derivative of 3e to the 3t. That's the definition of the product rule. This is like first times the derivative of the second plus the second times the derivative of the first. So I could say, oh, I recognize the product rule, and this will happen every time. So when you're doing this, it's not like recognizing the product rule is like some surprise, right? It's going to happen every time. So you should say, okay, this is the derivative of the product y times e to the 3t. First times the derivative, first times the derivative of the second plus the second times the derivative of the first. All that on the left-hand side. That's just written out using the product rule to have taken the derivative of y times e to the 3t. Right-hand side, I'm not doing anything to that yet. So now I can integrate both sides because integrating the left is easy. Right? Because what's the antiderivative of a derivative? Itself, right? So the left-hand side is just y e to the 3t. And then the antiderivative of t e to the 3t, what method of integration would I use for that? Yeah, it's what undoes the product rule in integration by parts. We can go over it afterwards, but I'm just going to write down what the integral is. It comes out to 1/3 t e to the 3t minus 1/9 e to the 3t plus c. And then the last thing we do is we solve for y. So you're just going to divide both sides by e to the 3t, and we have our solution. Y equals 1/3 t minus 1/9 plus c over e to the 3t. So you like it better than the 3-step lucky guess process? Yeah, a lot of people do. You do end up having to do sometimes some tricky integrations. This one's not that bad. Doing by parts on that guy's not too bad. But sometimes you get some really messy things.
So this always result in that sort of product rule and swing aside.
Yes, that's the key to the integration factor, is that it forces this product rule thing to happen.
Gotcha.
Yeah. So there are two integration steps, right? You have to come up with this integration factor. Sometimes that's hard. And then you have to integrate both sides, and sometimes that's hard. So sometimes lucky guess might actually be easier, but sometimes not. So yeah, we got plenty of time. Yeah, yeah. So what does that dy dt mean? That's, oh, okay. If you're thinking the product, so d dt of f times g, you would say f prime g plus f g prime. That's how you remember the rule. Okay, so then this is f prime, this is g, this is f, this is g. Prime, yes. Yeah, yeah, it's pretty neat. Okay, so let's quickly go over how to do that integration by parts. Just a quick review. The integral of t e to the 3t. I'll do it on a separate piece of paper. So typically when you see a product and u substitution doesn't work, you're going to use by parts. So by parts, that says that the integral of u dv is equal to u times v minus the integral of v du. So we have to choose a u and we have to choose a dv. So in general, choose dv to be the most complicated thing that you can still integrate, right? So e to the 3t is more complicated than t, yet I can integrate it, so that's what I usually choose. The more complicated thing, but that is still able to be integrated. And so, and then you have a dt on there, and then u is just t. And then you have to figure out what du and v are in order to apply the formula. So du is just dt in this case, because u equals t. And then v, that's the antiderivative of e to the 3t. So that would be 1/3 e to the 3t. And then we just plug into the formula. Okay, so u times v, that's 1/3 t e to the 3t minus the integral of v du. So that is 1/3 e to the 3t dt. Simplify 1/3 t e to the 3t minus 1/3, just pulled that 1/3 out of the integral. And then the antiderivative of e to the 3t is 1/3 e to the 3t.
it was like you set it up as like a 4 points, du, v, dv, u, du, like one on the other end.
Okay. And then a third times a third is
u, du, v, u, dv, v.
All right, so we're going to look at another mixture problem, right? So we talked about one in one of our earlier classes, and we're going to do one that has a little wrinkle thrown in this time. So we have a pond with an initial volume of 10,000 cubic meters, and suppose that at time t equals 0, the water in the pond is clean, and there are two streams flowing into it, stream A and stream B, one stream flowing out, stream C. All right, so we've got, suppose 500 cubic meters per day of water flow in from stream A. So I'm just going to take notes on my picture here. 500 cubic meters per day from stream A. And then 750 cubic meters per day from stream B. And then 1250, which is the sum of these two, right, flow out from stream C. At time t equals 0, the water flowing into the pond from stream A becomes contaminated with road salt. And the concentration is 5 kilograms per 1,000 cubic meters. And then suppose the water in the pond is well mixed, so that the concentration of salt at any given time is constant throughout the pond. And then to make matters worse, also at time t equals 0, someone begins dumping trash into the pond at a rate of 50 cubic meters per day. Trash settles to the bottom of the pond, reducing the volume of the pond by 50 cubic meters each day. So to adjust for the incoming trash, the rate that water flows out via stream C is going to increase to 1,300 cubic meters per day, so that the banks of the pond won't overflow. All right, so we want to write a model for S of t, which is the amount of salt in kilograms in the pond at time t. So we know some information about how S of t is changing. So we're writing a differential equation, ds dt. And just like our last rate problem, it's rate in minus rate out. Okay, so we want to figure out what is the rate that salt is entering the pond. Well, it's entering the pond through stream A, which comes in at 500 cubic meters per day. But that 500 cubic meters each day is now contaminated with road salt that has a concentration 5 kilograms per 1,000 cubic meters. So our rate in is the rate of the water, 500 cubic meters per day, times the concentration of salt in that water, which is 5 kilograms per 1,000 cubic meters. And I like to write the units out because then you see the cubic meters cancel and you go, okay, kilograms per day. That's what I'm looking for. Kilograms of salt per day. That's a rate of how the salt is changing, which comes out to 2.5. Yeah. All right. And then the rate out, it's all the salt is leaving through stream C, and stream C flows at 1,300 cubic meters per day. And then I have to multiply times the concentration of salt in that water. So we'd have to, the concentration is the concentration of the total salt in the pond, which is the amount of salt in the pond divided by the total amount of water in the pond. Right. Okay. So how much salt is in the pond at time t? It's 0 at 0, and then it's changing with time, right? And that's actually what we're studying, right? That's S. S is the amount of salt in the pond at time t. So I'm going to put an S up here. S kilograms of salt are in the pond at any given time. And then I need to know how much water is in the pond at any given time. How much water does the pond hold? Yeah, 10,000, but then it's being reduced by 50 per day. No, simpler than that. So it's 10,000 minus 50 each day. So minus 50 T. And that's cubic meters in the pond. So again, the cubic meters cancel and you get kilograms per day. And then we simplify and you get 2.5. I'm just going to leave out the units for right now. 2.5 minus 26S over 200 minus T. And then my initial condition, Keith just said it, how much salt was in the water at time T? 0. The water was clean, so S of 0 is 0. It's my initial condition. So that is my initial value problem for this stream. That is the amount of water in the pond. Right. It started out holding 10,000 cubic meters, and then you're losing 50 cubic meters of space every day because trash is going in. So I did the multiplication. So I had 1,300 over 10,000 minus 50T, and then I just reduced the fraction. Yeah. This is funny that you're all asking me this arithmetic question. Okay, so I have 1,300 over 10,000 minus 50T. So in the denominator, I factored out a 50. So I have 50 times 200 minus T. And then I reduced. I said, okay, well, 50 goes into 1,350 once and 1,326 times.
Algebra.
Yeah, it's just algebra. You probably all thought I did something fancy, but. Oh, okay. Because stream B never got contaminated. There's no salt coming in through stream B. Even though it's just like adding extra water to take care of that. Right. Right. Yeah, because what we were writing was an equation for how the salt is changing. So stream B doesn't change the salinity at all because no salt is entering and no salt is leaving that way. Yeah. All right, so in your class activities, which we're going to be doing at the start of next class, you're going to solve that initial value problem using an integrating factor. But for now, I just want to look at the slope field and sketch a solution for our initial value, which was S of 0 equals 0. So there's our initial condition. If I try to follow the slope field, it does something like, it's very, very steep, right? And let's remember that this is T and this is S of T, right? Time and the amount of salt in the pond. So the amount of salt in the pond is going up, 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 and then it seems to turn around and come down, right? So does that make sense with this situation? That the amount of salt in the pond, it becomes very, very, very salty, right? And then it decreases down to, seems like 0. The body, it filled up with trash. There is no more water in the pond, so there is no more salt in the pond either, right? Yeah. No?
I mean, if you're going to start introducing salt, zero, at a specific rate, volume, salt in the jar should increase with time, slowly, then slowly. Trash.
I mean, it's going to reach an equilibrium point at whatever the concentration of the salt is in the environment.
Well, how does it do so fast?
Hmm.
A lot of trash. 52 feet a day.
I guess
Well, we're talking about salt. We're talking about how much salt is in the pond, right? So the salt enters at 2.5 kilograms per day, right? I don't know. Well, maybe it's just the scale here because this is days, right? So like 20 days for it to hit a peak, maybe.
So it'll hit pretty much the top that is the saturation.
Yeah.
Decrease goes as the
Yeah,
saturation.
then the water starts to flow. Well, it's the same rate, but there's just the pond's just holding less water. Yeah. Right, but that 1300 stays constant. Yeah. Yeah, I was looking at that earlier. Yeah, it does kind of look like maybe it starts to go back up. Does it do that? Yeah. So that the salt looks kind of like the salt spikes and then goes down and then goes way up. I might have broken the model. That happens. And it might be that I'm just not following the slope fields well. So let's this might be a good opportunity to show you how GeoGebra can do some of these things.